Good morning. Happy Monday. Wanted to go through our next section, just get it started. We'll go through the second piece tomorrow in class, so make sure you watch the video, which would be terrible to tell you if you don't watch it. So there we go. Today we're going to be talking about the trapezoid and Simpsons rule. Now these are designed specifically to talk about functions and areas that are impossible to find with standard integration techniques due to the fact that the integrals of them may not exist. And so they list some examples in the text right here about how these pieces kind of fit together. These are some elementary functions whose integrals do not exist. They just don't. And so we'll talk about these rules as faster ways to find out how to find the integral values because they are much faster than doing them by the standard limit tests. So let's look at our first theorem of the day. The book does a great job of illustrating why they're called the trapezoidal rule and why they're called Simpsons rule. Feel free to take a look at these little sections, these little proofs here. They're great. But I want to focus on theorem 417, which states, let f be continuous on the interval from a to b. The trapezoidal rule for approximating the integral from a to b of f of x dx is given by this function. Now, the important thing to note here is in two parts. Number one, that the f of x terms are, again, listed out in n form, so they're raising in value as we go, and that the coefficients of them, the numbers in front of them, follow a specific pattern, which is listed right here in the note. The coefficients for the trapezoidal rule start as a coefficient of 1, and then transition to a coefficient of 2 until they are 1. Now, in the book, they show this example of an integral being done with the trapezoidal rule, one that's easy to check with standard integration technique. I'm going to do the exact same thing for a different integral, so you get a couple different examples of them, where I will use the trapezoidal rule to find the solution that could be done without the trapezoidal rule. So in this case, I'm going to do the integral from 0 to 2 of x squared dx. I'm going to do it twice. Once where my n is equal to 4, and a second time where my n is equal to 8. And so we're going to go through this process a couple times, showcasing the trapezoidal rule as we go. All right, let's begin. The trapezoidal rule states we will do the integral from a to b of f of x dx is equal to b minus a over n times f of x sub 0 plus 2 f of x sub 1 plus, and then continuing to 2f of x sub n minus 1 plus f of x sub n. So what we're going to do is we're going to supplement this function now with our n of 4 and our n of 8. So to do this, let's try it out. So this time, n equals 4. So we have b minus a over n, so that would be 2 minus 0 over our n. Wait, sorry, make sure it's correct. The trapezoidal rule has a 2n on the bottom. So in our function, we're going to do 2 times 4. And then the next piece is doing f of x sub 0, f of x sub 1, until we get to f of x sub n. Since n is 4, that means there's going to be 4 rectangles, which means we're going to be looking for a total of 5 values. Because remember, these are the values that surround the rectangles, not the actual values themselves. And so there'll be 4 rectangles with 5 values around them. Think of the function, in this case, as the following picture, with our x squared. Beautiful. So I want to break it into 4 rectangles. I've got 2 rectangles, 4 rectangles. I'd have 1, 2, 3, 4, 5 values for our function. So there we go. Let's try it out. So I'd have f of x sub 0 plus 2f. Now, the number that goes in here needs to be based upon our delta value. So we're going to go back to what we talked about back in section 1 of b minus a over n for our delta value. In this case, our delta would be 2 minus 0 over 4. So that would be 1/2. So what's going to go in here is the original value of 0 plus our delta value. So what goes in here is 1/2. The next one, you just take that delta and add it again. So this becomes 1. And then finally, the last value is there. So we have a total of 5 values, 1, 2, 3, 4, 5 values, exactly as predicted. The first value is our A, the second value, or the last value is our B, and each value is separated by our delta of 1/2. So let's figure out what this is. So B minus A over 2n, so B minus A, so 2 minus 0 would be 2 on top, over 2 times 4, which would be 8. So we end up with 1/4 out front. And what we plug in here is our 0 into our original function x squared. So we do 0 squared plus 2 times 1/2 squared plus 2 times 1 squared plus 2 times 3/2 squared plus 2 squared. So notice how the first term and the last term have no coefficients, they're ones, and every term in between follows 2's. And so now we do 1/4 times, okay, 0 squared is 0. 1/2 squared is 1/4 times 2 is 1/2. 1 squared is 1 times 2 is 2. 3/2 squared is 9/4 times 2 is 9/2. Plus 2 squared is 4. And then we add all these pieces together and times it by 1/4. So 1/4 times, let's see, 1/2 and 9/2 makes 10/2 or 5. 0 plus 5 plus 2 plus 4 would make this 11. And so we end up with a value of 11 over 4. Which is beautiful. Or equivalently 3.75. It turns out this is actually pretty close to the actual solution, but now we're going to do part 2. So this was all part 1, where we have n equals 4. Now we're going to do the exact same thing now, but with n equals 8. So now, part 2, n equals 8. Now since we have a larger n value, there's going to be more of these middling terms in here. But as we go through, I'll make sure to do our delta term, do each term in between having a value of 2 for the coefficient, outer values having a coefficient of 1. Everything will fit together very nicely. So here we go. So b minus a over n. So 2 minus 0 over 2 times n, parentheses. All right. Now our delta is going to be b minus a over n, which would be 2 minus 0 over 8, or 1/4. So now our numbers that are going to be plugged in here are going to go up by 1/4 each time. So we're going to have f of 0 plus 2 f of 1/4 plus 2 f of 1/2. Notice each time it's just going up by 1/4. 2 f of 3/4 plus 2 f of 1 plus 2 f of 5/4 plus 2 f of 3/2 plus 2 f of, oh my gosh, 7/4 plus f of 2. And there's our function. So this is again the trapezoidal rule. Now we've got our pieces all lined up into our formula. We have our outer piece, which is b minus a over 2n, and now it's simply a matter of simplifying. So again, this number is 3.75, which I tell you is close to the actual solution, but let's see what it actually is better. With a higher number for n, we should get a more accurate solution. So let's see what happens. 2 minus 0 is 2, divided by 2 times 8 would be 16, divided by 16 would be 1 over 8. All right. So now I plug in 0, 1/2, 1/4, 1/2, 3/4, and so on. This would be 0 squared plus 2 times 1/4 squared plus 2 times 1/2 squared plus 2 times 3/4 squared. So again, this is just plugging our number into our original equation. Plus 2 times 1 squared plus 2 times 5/4 squared plus 2 times 3/2 squared plus 2 times 7/4 squared plus 2 squared. So 1/8 times, okay, so 0 squared is 0. 1/4 squared would be 1/16 times 2 would be 1/8. 1/2 squared is 1/4 times 2 would be 1/2. 3/4 would be 9/16 times 2 would be 9/8. 1 squared is 1 times 2 would be 2. 5/4 would be 25/16 times 2 would be 25/8. 3/2 would become 9/4 times 2 would be 9/2. 7/4 would be 49/16, which would be 49/8. 2 squared is 4. All right. In theory, this value should be real close to the actual value, which we're going to find the actual value at the very end to verify that we are doing this correctly. So we'd have 1/8. So we have 1/8, 9/8, 25/8, and 49/8. So 1 and 9 would be 10, 35, 84. So we end up with 84/8 plus 1/2 and 9/2 make this 10/2, which is 5. 0, 2, and 4 would make this 6. Okay, so for this would be 21/2 plus 11. All right, just going through the process of simplifying now. 21/2 plus 11, that'd be 22/2, so it gives us 42/2 times 1/8, which gives us 42/16, which would give us the decimal value of, if you divide that by 2, that'd be 21/8, which would be 3.625. That's pretty dang good. Now let's determine the actual value. So we're going to integrate this function. In theory, it should be really close to this number. So the integral from 0 to 2 of x squared dx, which is 1/3 x cubed, from 0 to 2. We plug in 2, we plug in 0, so we get 1/3 times 2 cubed minus 1/3 times 0 cubed. This would be 8/3. Can I not math? Oh my gosh, I can't math. I'm so glad you guys aren't here to yell at me. Alright, it should be 2.625. Okay, this ends up being 2.66 repeating. So that's pretty darn close. So with a value of 8, we got within 1 decimal place. That's pretty darn good. Which was more consistent than what we got in the previous sections, going up to 16 decimal places. So that's pretty nice. So this is the trapezoidal rule. It's a simple function to use. It just has some weird quirks to it. The weird quirk being, first of all, the number on the outside, b minus a over 2n, as opposed to b minus a over n, which is a typical delta formation. And then this fact that the f's increase the coefficients to 2 for every term except the first and last. Now, the Simpsons rule is very similar to this, with one small exception. The function that we plug it into is a little bit different. And so let's look now at our next theorem. And again, there's another version of this here in the book, and you can actually see that they went through the same process with 4 and 8, and they found that it got very close to the actual value of 2. By the time they got to 8, it was again within 1 decimal place, which is pretty nice. Now let's talk about the Simpsons rule. Theorem 418 is not necessary for your homework. It's just a faster way to be able to do an integral of a simple power rule. It gives you a nice function, which is pretty neat. Again, it's kind of nice. And especially if you don't know what the function itself is, you can kind of work this thing out and figure out A, B, and C separately with this kind of function. Let's look at the Simpsons rule, which is Theorem 419. So Theorem 419 works a little bit differently than the other theorem. It has a couple of things that are a little bit different. So first of all, instead of b minus a over 2n, it's b minus a over 3n. That's a big difference. So instead of 2 on the bottom, it's a 3 on bottom. And notice that the coefficients, if you do the note down here below, are 1, 4, 2, 4, and they alternate between 4 and 2 until the last term, which is back to 1. So again, we're going to be applying this exact same problem to our x squared example. And the Simpsons rule is even faster at getting to the right solution than the trapezoidal rule, which again was even faster than finding the right solution by the standard rules. And so again, as this function approaches infinity, it will approach the actual value. And so this is one that is typically used by mathematical theorems to find the actual value very quickly, as opposed to needing to use one of the other rules. So let's go through our example again. So our formula is the integral from a to b of f of x dx is equal to b minus a over 3n times f of x sub 0 plus 4 f of x sub 1 plus 2 f of x sub 2 plus dot 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 4 f of x sub n minus 1 plus f of x sub n. Alright, here we go. We're going to do the integral, just like before, from 0 to 2 of x squared dx. Alright, I'm going to do it twice. Once with n equals 4, and again with n equals 8. First time, n equals 4. So, first of all, let's go ahead and figure out our delta. So, again, we plug in b minus a over n. So, that would be 2 minus 0 over 4, which would be 1/2. So, that's how we're going to count our values. And so, this integral is going to be equal to b 2 minus a 0 over 3 times n, so 3 times 4. So then we plug in with our delta, our first one, that'd be f of 0 plus 4 f of 1/2 plus 2 f of 1. Notice that again our values are going up by our delta, plus 4 f of 3/2 plus f of 2. So there's my function. 2 minus 0 is 2, divided by 3 times 4 is 12, so that ends up being 2 over 12, which is, of course, 1 over 6. F of 0 is 0 squared plus 4 times 1/2 squared plus 2 times 1 squared plus 4 times 3/2 squared plus 2 squared. 0 squared is 0. 1/2 squared is 1/4 times 4 is 1. 1 squared is 1 times 2 is 2. 3/2 squared is 9/4 times 4 would be 9. And then 2 squared is 4. So we end up with 1/6 times 0 plus 1 plus 2 plus 9 plus 4 is 16. So we end up with 16 over 6, which is 8 over 3. which it turns out is the correct solution. So with n equals 4, we actually end up with the correct solution right off the bat, which is pretty unique. It's actually a consequence of how the Simpsons rule actually works. It works really well with functions that are, polynomial functions. All right, let's do it again with n equals 8. But since we already have the right solution, we should already know this is going to be really good. Our delta would be b minus a over n. So 2 minus 0 over 8, which would be 1 over 4. All right, let's do it. So 2 minus 0 over 3 times 8, parentheses. All right. Oh my gosh. You calm down. There we go. So we would do f of 0 plus 4, f go up by a quarter, so that'd be 1/4, plus 2, f of 1/2, plus 4, f of 3/4, plus 2. Notice again, the first one is a 1, then 4, 2, 4, 2. And we'll continue this pattern until we get back to 4 and then get back to 1. F of 5/4 plus 2, f of 3/2 plus 4, f of 7/4 plus f of 2. All right, let's plug them in. So for this function, let's stick with the first piece. 2 minus 0 is 2. 3 times 8 is 24. 2 over 24 is 1 over 12. There we go. Times. This would be 0 squared plus 4 times 1/4 squared would be 1 over 16. Plus 1/2 squared is 1/4. Plus 9 over 16. Plus 2 times 1. Plus 4 times 25 over 16. Plus 2 times 9 over 4. Plus 4. 49 over 16 plus 4. All right, looking good so far. Now let's start simplifying. 0 squared is 0 plus 4 times 1 over 16 would be 1 over 4. 2 times 1 over 4 would be 1/2. 4 times 9 over 16 would be 9 over 4. 2 times 1 would be 2. 25 over 16 becomes 25 over 4. Let's see, 9 over 4 becomes 9 over 2, which becomes 49 over 4 plus 4. Good so far. And then we just start simplifying. Okay, here we go. So 1 over 12 times, all right, so let's take care of the nasty ones. The 4s, 9 over 4, 25 over 4, 49 over 4. This becomes 34 plus 49 plus 1. So it'd be 10, 35, 84 over 4. Nine halves and 9 halves becomes 10 halves, which becomes 5. 2 and 4 becomes 6. So we end up with 1 over 12 times, let's see, 5 and 6 makes us 11. 4 divides into 84, leaving me with 21. So we end up with 21 plus 11. This ends up being 1 over 12 times 32. 32, when I divide it by 12, becomes 16 over 6, which becomes 8 over 3. Wow, look at that. The exact same solution. It's almost like it's supposed to work. So, this is how the trapezoid and Simpsons rules work. They're just slight deviations from each other based upon these two theorems, Theorem 419 and Theorem 417. Most of your homework problems deal specifically with doing these. There are a couple that deal with how to use the error of these, and we will focus on that piece tomorrow. We'll also redo another Simpsons and trapezoidal rule for each one of these, so you can see them work again with a different function that is not just x squared. Note the differences between the trapezoidal and the Simpsons. This term right here is really big. The b minus a over 3n as a b minus a over 2n, and then the alternating pattern of 4, 2, 4, 2 as opposed to 1, 2, 2, 2, 2, 1. So there we have it. There's all of our pieces, and I'll talk to you guys tomorrow. See you then. Bye.